Einstein's theory of general relativity gives us a lens through which we can understand this strange behavior. In general relativity, space isn't just some background in which other things can move around. Instead, space itself can stretch and warp and evolve over time. Einstein showed that in this framework, gravity is no longer a force, but rather a distortion of an object's inertial path in a dynamical spacetime. For example, when a planet orbits around the Sun, in Einstein's description, it's merely following a straight-line path in a curved space. By the same token, what we observe as a repulsive force between galaxy clusters should really be thought of as an accelerated stretching of the space between them. But what could possibly cause the expansion of space to accelerate like this on the largest scales of the universe? To begin to answer this question, we need to know what causes space-time to stretch and warp to begin with. One of the first things you might learn in a physics class is that gravity is an attractive force between two objects whose strength is proportional to each of their masses. Gravity keeps planets locked in orbit around the Sun. It keeps stars grouped together in the Milky Way, and it even attracts galaxies together to form galaxy clusters and superclusters. But if we zoom out further, this gravitational attraction begins to act in reverse, causing galaxy clusters to accelerate away from each other rather than drawing each other in. So what's going on here? In Newton's theory of gravity, all objects with mass exert a gravitational pull, and in general relativity, all objects with mass curve the space-time around them. But Einstein showed that in addition to mass, any form of energy or pressure will also influence the dynamics of space-time. Energy density is how much energy is found within a given volume, how much pop, heat, zap, and motion exists within a given space, and in our universe has always been found to be positive. Pressure is how much force over an area the contents of that space sends pushing into the rest of the universe around it. Think interstellar dust pushing on each other whenever they bump into each other in the void. As you can imagine, for objects so far apart, this pressure value hovers a little over zero on a cosmic scale. When these values are cumulatively positive, as in the following formula, their influence on the space around them causes the space around them to contract in. Essentially, they create gravity by decelerating the stretching of space. However, conceivably, if you were somehow to set the values of this equation so that pressure was negative and greater than the positive energy density, that minus sign would cause the whole thing to flip, and you would accelerate the stretching of space. In effect, you would end up with a volume of space filled with a kind of anti-gravity, a dark energy. It's a little nebulous, as it's tricky to visualize anything with a truly negative pressure. How can you have less than zero atoms in a patch of space after all? But atoms are not the only things that exerts pressure. After all, pressure is simply a force applied across an area. Fields can also apply forces. Think a magnetic field dragging a piece of iron in towards a bar magnet or two magnets pushing each other away. If dark energy were some kind of field that pushed away not just other magnets, but everything, then this would match what we see the universe doing. Vacuum itself having dark energy and enough of it to slowly, very gently push the universe apart. Scientists have thought a lot about dark energy over the years and have even figured out what its combined energy density and pressure needed to be to create the rate of spatial expansion that we witness. It's around 10 circumflex 9 in SI units, which is a very small number, which is why we don't usually notice it here on Earth and only spot it on the grand cosmological scale of the universe. This is actually good news, because it turns out that if the number was much higher or lower than this, things would get very bad for our chance of existing. Let me show you what I mean with a quick sketch of the history of the universe. Here is the full history of the universe, from the moment just after the Big Bang to the present. This is the dark energy density as measured by astronomers. Scientists believe its negative pressure has kept this density roughly constant for billions of years. This is the density of ordinary matter in the universe, which has little to no pressure. The density decreases over time because the expansion of space dilutes the matter within it. Finally, this is the density of radiation in the universe, including photons and other extremely light particles. The positive pressure of radiation makes it dilute away even more quickly than ordinary matter. Towards the beginning of time, for a very short period, there were no atoms. Very quickly, though, protons and neutrons fused together to create the first atomic nuclei in the very early universe. Shortly after, matter took over as the dominant form of energy, beating out radiation. The universe cooled down enough for nuclei to attract and hold onto electrons, forming the first atoms of hydrogen and helium. These atoms were the building blocks for the very first stars, and these stars were pulled together by gravity to form the very first galaxies and clusters. Only later did dark energy take over, triggering the accelerated expansion of space and preventing the formation of larger structures. But what would have happened if the energy density were larger? Consider what would have happened if the pushing force of dark energy was stronger. It could have been enough to halt the formation of those early galaxies, pushing apart stars more powerfully than their own gravity could pull them together. A bit larger than that, and it would have been much more difficult for any stars to form either. And if the dark energy density were large enough, we would hardly have had any atoms or even nuclei produced in the universe. So that's what it could have been. Our existence so far appears to be excessively fortunate. Our existence is surprising. Perhaps that means the universe has more surprises in store for us. How do you think it happened? Leave your answer in the comments below. And subscribe to our channel for more similar videos on space science and education.